So we can always start with a super simple question. In our work, we can look at the hydrogen problem, right? H2. H2 is really easy. That's where we'll begin. Two hydrogen 1s orbitals stacked up next to each other. They look like they're circles, and then of course we get our molecular orbitals, psi1, psi2, put in our electrons, and see that old chestnut. We've seen this picture a million times. Psi1 is the in-phase combination. Psi2 is the out-of-phase combination. Okay, piece of cake, right? Well, lucky for us, that piece of cake is useful for moving on into bigger systems. So let's first think of something simple like H3. Okay, H3 has two possible shapes. Did you know that? Well, you know you can make two types of shapes with 3 points. One of those could be a line, the linear form, right? So here's H3 linear. Let's try that problem first. So if we put three 1s orbitals all next to each other, how would we make a molecular orbital diagram for this in a quick and easy way? Well, the first thing we want to do is consider our symmetry. Boy, I'm blanking out here. Our symmetry related atoms, there we go. Right, the central atom is different in symmetry from the outer two atoms. So we'll consider the outer two atoms together first, and we can combine those in a set just like we always have with two hydrogen 1s atoms, an in-phase and an out-of-phase pair. This time they're not combining because they're not geometrically related to each other, right? This one's too far from that one, so that's easy. Okay, so we're going to start with, so this gets broken down into two smaller problems. The first problem is the outer two atoms, where we'll have an in-phase combination and an out-of-phase combination. Okay, what do we call those? You might remember, these are our symmetry adapted linear combination with a little bit less fancy symmetry going on. You might even recall that this would be maybe like an A1 and a B2 or something like that, depending on which point group you chose for this linear problem. Okay, great. So we have two salcs, and now we need to get our central atom involved. Okay, and so in order to do that, we'll go ahead and say we can combine one of these two salcs, which has the proper symmetry, with our 1s orbital, and that's of course this one on the bottom. Okay, so the next arrow is the second part of the problem. Okay, so we can combine an in-phase combination to make the all in phase. I should have made that one twice as large. So here we'll shade them all. There we go. I don't have to worry about that. Okay, why is it twice as large? Because we have split these two up between two different salcs. Okay, so half of the 1s orbital on the right here is being used in the bottom salc and half in the top salc. Whereas in this case, we have the entire 1s orbital to be used here. Okay, so then we go ahead and do our out-of-phase combination. Where now the outer two are shaded, the inner one is unshaded. That would be an antibond. And what do we do with our B1 salc? Well, that does nothing, right? That does not have the proper symmetry to have overlap with that middle one. And as it turns out, that's exactly what our bonding picture looks like. How do we do this with our energies? Well, we have two salcs over here. They have the same energy. Okay, and then we have our other central 1s orbital there, and then they combine, one bonding, one antibonding, combination, psi1, psi2, psi3, of course psi2, because it comes straight across in energy, is our non-bonding combination. When we put in our electrons, we see that we have a semi-stable molecule here with a single electron in a non-bond, albeit a radical, so that might decrease the stability somewhat, but we have a bonding combination filled and the antibond completely unfilled. So a reasonably stable molecule. In fact, if you can make the H3 plus ion, you might expect linear hydrogen to be quite stable. I challenge you to go ahead and try this and just keep extending that hydrogen chain longer and longer and longer and see what happens. You might find yourself thinking of a material called metallic hydrogen, which is very cool, and I encourage you to look up for various purposes. Some science papers have been written about that recently. Okay, so that was one of the possibilities for H3. What's the other H3 possibility? Well, if we go all the way to the other bookend, the other possibility would be a triangle shape. For here, we would have our 3,1s orbitals in this orientation, something like this. How would we go ahead and solve this problem? I'll give you a second to think about it. Okay, again, start with what you know. All right, let's call this A, B, and C, just to keep it all straight. Okay, so start by, again, break it down into two easy problems. Start by premixing A and B. Okay, what happens if we premix A and B? Well, we have a problem that we definitely know how to solve because it looks like this. Okay, so A and B come together. We gotta go ahead and get two orbitals out of that. We'll have A, B. This is exactly the same as the normal H2 problem. One bonding, one antibonding combination. And we could go through and even do the symmetry labels of this if we really wanted to, but we don't really need to worry about that. Let's just call it sigma star, because those are very clearly bonding and antibonding. Okay, now we got to mix in our C. Okay, and how can we do this? Very similar to our linear problem. When we think about this, we would take our fragments here, our AB fragments that we've already put together. You could even call them salks if you wanted to, but they're actually molecular orbitals now because there is overlap. So we get our two orbitals here, what we were calling sigma star. These have two electrons, none up there. And then we think about where is the energy of our third orbital. Well, of course, that should be halfway between the two because that's where they started. Okay, so we call this our C orbital, has one electron in it. Okay, and now we can think about what happens with these orbitals. Our C orbital, the one located here, can mix with sigma, but can't mix with sigma star. Your G and U labels would help you figure that out, or other ones, if you were in C3V or D3H, whatever point group you chose for this molecule to work this problem. Okay, so what we can see though is that C can overlap with our sigma orbital, but not our sigma star. So sigma star comes straight across. Sigma goes down in energy by mixing with C. And then of course, we got that equal amount there coming up here. We'll put it right about there. Not going to be too picky about this. To get our resultant molecular orbitals, put in our electrons, and there we go. So, oh, and what would that look like? Of course, we can draw those orbitals, right? So this bottom pair is, of course, the AB combination plus a bigger component from C. That's why we stabilize that quite a bit. And then of the top components, we still have our AB antibond with nothing in the C position, and our AB in phase with the C out of phase. You might make the argument that the component of C is so much larger here that it would be higher in energy. Think about those of you who enjoy the math, think about the geometry involved in this overlap equation, right? Is the overlap here greater than or less than the overlap here? Based on the coefficients of those two orbitals and the shapes of their overlaps. It's a tricky question, but kind of a fun one to consider if you want to go deep. Okay, let's compare then the results from our linear problem and our triangular problem to see which one would be better. Okay, so the results of our triangle problem, sorry, our linear problem, 3 equally spaced levels, and we'll call this one 0. That was the starting energy of our hydrogen 1s orbitals. Okay, and of course, can populate those. And then in the case of our triangular form, we're stabilizing sigma and then stabilizing it a second time. So that's actually going to have a lower energy down here. So this is our linear triangle. These are our MOs down here. Okay, so our triangle is over here, more stabilized in the bonding, but then our antibonds are obviously going to be destabilized from the non-bond that we had in the linear form. So we have a more stable sigma bond, but some destabilization by populating the antibonding combination here. So these are our sigma star, sigma, sigma, and B, sigma star. You can even go ahead and draw these pictures again. This one, that one, that one, this one here, looks like that. And then we have our antibonds. So the question might arise, which one is the preferred solution? We have 2 solutions here. Which one would be better? It's kind of hard to say exactly, right? You might need to do the actual computation using DFT methods to actually dig in and find out, is the stabilization here greater than the destabilization there? I'm going to lean, however, towards the triangular form because there's 2 electrons in this more stabilized orbital and only a single electron in the destabilized orbital. So you're kind of getting twice as much money for your bang for your buck. So, okay, so that's the H3 problem. Now, got some very cool things that we can do using this. So let's dig in a little further. We've got a cyclic molecule. We did H3, and I'm going to give you a super fast shortcut for cyclic molecules, and this works for all of them, and then I'm going to show you how to use that to even extend to pi systems. So for triangle H3, our results found us 3 orbitals, and they had energies that ended up like that. Okay, so we can do something called the Frost circle. Okay, where we take our shape of our cyclic molecule, in this case, the triangle, you put it on one of the vertices, you put it on a point, and then you put orbitals, energy levels, at each point, each vertex, and that gets you your molecular orbital diagram. It is really that easy. Okay, so what would we predict using a Frost circle for H4? Cyclic H4. Okay, so that is a triangle. Sorry, not a triangle, it's a square, right? A square. And if we want to do a Frost circle, we would put that into a diamond shape like so, okay, which would produce an MO diagram with 2 non-bonding orbitals, a bonding and an antibond. That's pretty interesting. I guess we're gonna have to do this H4 problem, aren't we? All right, okay, well, let's go ahead and dig in on that. So how do we do cyclic H4 in a reasonably quick fashion? Well, we have 4 orbitals. Let's break it down into 2 smaller problems. I'm going to go to the square that's not on its vertex now. So I'm going to say we've got, start over here. So we've got 1 orbital here. We've got 1 here, 1 there, and 1 there. Maybe call that A, B, C, and D. I'm going to regret the way I named those in just a second. Now we can make this work. Okay, so first let's combine A and B together. Right, those are next to each other, and let's solve a very simple H2 problem for us to do that, right? So A plus B, we start with A, B, form bonding and anti-bonding combinations. One that looks like that, the other, which looks like this. Hopefully you're with me so far. Okay, we could do the exact same thing for C and D. Let's do that in our minds, but without doing the full representation here. So I'm going to put those two over here. Okay, great. So now we need to consider which of those can combine with one another. Well, they all could combine. So the easy one, the all in phase combination, we know what to do there. We form a nice bonding orbital, our lowest energy orbital, piece of cake. We can also, if we then combine together, we have to combine, make the opposite combination. So in phase, we now have an out of phase combination. That's going to raise an energy, which is going to look like one side shaded, the other side not shaded. Okay, now let's try these two up here. The in phase combination will have shaded, unshaded, shaded, unshaded, our highest energy orbital. The all out of phase combination. And the in phase combination, this minus that, means the bottom two will be in phase, the top two will be out of phase, and we're going to put that at exactly this energy, and we'll see why right here. Okay, so the bottom two are shaded, top two are not. You see we have exactly one node through this molecule here and one there. These two have the exact same energy. They are a degenerate set that are orthogonal to one another. Okay, so our resultant molecular orbital diagram down the middle here with the pictures that go along with it. 1, 2, 3, and 4. Sorry, we'll do psi 1, psi 2, psi 3, psi 4. Does give us, in fact, our frost circle predicted picture. So that's pretty clever. And in fact, I'd give you a clue as to how to do this even more quickly without having to do this problem every time. For a cyclic molecule, you do your frost circle, you count the number of nodes, the 0 nodes at the bottom, 1, 2, so on all the way up as you go, right? So the nodes here in psi 4 go through the middle that way and that way. Okay, so your challenge now is to go to the chromium problem that I gave you and think about those aryl rings, those benzenes, and go ahead and consider how do those benzenes interact with the chromium. Well, in order to do that, we need to think about a pi system first. So let's think of a different pi system. Let's think about cyclobutadiene. Looks like this, right? So really quick, just going to go back. So for a chromium problem, consider benzene. Okay, that's for you for next time. As a hint, we'll do cyclobutadiene down here. Okay, we can jump ahead. We'll use our frost circle to make a diagram that looks like this. And you'll say to yourself, well, now wait a second, you should have sat for hydrogen atoms. Those are sigma bonds, not pi bonds. Check this out. It also works for pi bonds. Okay, so we've got this same picture. We can remember the number of nodes. We'll borrow these solutions from the H2 problem, the sigma bond problem up here. The bottom one, if it looks like this for cyclobutadiene, well, if we're thinking about a pi system instead, each of these, what were s orbitals in this problem, now represent the top of the plane of the molecule in the p orbitals. In other words, these are 4 p orbitals all in phase. So the bottom one should then look like, try to draw this the best I can here. 4 p orbitals with their bottom halves shaded and their top halves unshaded. Okay, if we did our top orbital on our frost circle, we have opposite phasing all the way around. So then, of course, top, bottom, top, bottom, like so. And then these two, we could do this way, here or here. That would work just fine. And if we do that, we will see we have the two bonds that we would need in our resonance structures, essentially, to find that this is, right, we have two resonance structures of our cyclobutadiene, where the pi bonds go like so. Some of you are like, hey, it's anti-aromatic. Don't at me. It's cool. We're just doing some practice problems here. In phase up there, out of phase down here. So now, if that orbital is populated, we have a node between the two. That would be this representation, where we have a double bond on the two right and left side bonds, but the top and bottom bonds do not. I'll extend this one over here. The opposite one, of course, then has shading going the other way. So the back two are shaded up, the front two are shaded down, thus leaving us our node kind of cutting this molecule in half, leaving a top and bottom half. So that one would match up with this, right? So we call this Psi1, Psi2, Psi3, Psi4. Psi1 has all four carbons bonded together. Psi2 bonds these two together, the Psi3 down here. Now, how do we populate our frost circle? Well, in the case of pi bonds, we just count the number of pi electrons, 2, 4. 1, 2, 3, 4. So which one is it? Is it a double bond between the top two and the bottom two, or a double bond between the left two and the right two? Well, we know it's a resonance structure between the two, and as it turns out, that's what we see here as well. We have a half of a pi bond, or half of a pi bond between the bottom two and the top two, half of a pi bond between the left two and the right two. Interestingly, we'll get back to anti-aromaticity now. The reason that this structure is anti-aromatic is because this gains no stability by having these double bonds. These are non-bonding orbitals based on our frost circle, and if you do the math, right, these are equally bonding and anti-bonding combinations, both Psi2 and Psi3. Okay, so that should give you enough to go with to start working on how that thing bonds to the chromium, and for us to dig in on Tuesday to some more of the organometallic types of bonding that we might be interested in. If you have questions, feel free to email me before Tuesday. Otherwise, I want you to make sure you try the frost circle for benzene or some other aryl species. Try to draw out all the pictures of all 6 orbitals involved, this time using the pi structure. Consider where the electrons go, consider the energies, see if you can get a little bit more insight into some organic molecules using the molecular orbital theory tools that we have. Hope you enjoyed the video.